Imagine a computer that can solve problems thought to be impossible, tackling challenges that are currently beyond our reach. Problems like designing new life-saving drugs, creating revolutionary materials, or even cracking the most complex codes. That future isn't science fiction. It's the promise of quantum computing. But what exactly is quantum computing? It sounds intimidating, right? Don't worry, we're going to break it down. In this video, we'll explore the core concepts of this revolutionary technology in a way that's easy to understand, even if you don't have a background in physics or computer science. We'll unravel the mysteries of qubits, superposition, and entanglement, showing you how they unlock a new dimension of computational power. By the end, you'll have a solid grasp of the basics and understand why quantum computing is poised to change the world. So, buckle up, and let's dive into the quantum realm. So, how did this mind-bending field of quantum computing actually come about? It's a story built on the shoulders of some seriously brilliant minds, grappling with the weirdness of the quantum world. It all really kicks off in the early 1980s with physicists like Paul Benioff and Richard Feynman. Benioff showed that computers could, in principle, operate using the laws of quantum mechanics. Then, the legendary Feynman, never one to shy away from a challenge, pointed out that simulating quantum systems with classical computers was proving incredibly difficult, maybe even impossible. He boldly suggested that we needed computers built on quantum principles to tackle these problems. Think of it like trying to build a skyscraper with Lego bricks. Eventually, you need steel. David Deutsch really propelled the field forward in 1985. He described the first universal quantum computer, a theoretical machine capable of performing any computation that a classical computer could, but with the potential for vastly superior speed in certain areas. It was a game changer, shifting quantum computing from a theoretical curiosity to a tangible possibility. Then, in 1994, Peter Shaw dropped a bombshell. He developed an algorithm, now known as Shaw's algorithm, that could factor large numbers exponentially faster than the best-known classical algorithms. Factoring large numbers is the basis of much of modern cryptography, meaning Shaw's algorithm had massive implications for security. Suddenly, quantum computing wasn't just a cool physics problem. It had real-world applications that could reshape entire industries. Following Shaw's work, the race was on. Researchers like Love Grover developed algorithms showing quantum speedups for searching unsorted databases. Building on these theoretical foundations, the late 90s and early 2000s saw significant progress in building actual quantum computers. Albeit small and rudimentary, scientists around the globe are still pushing the boundaries of what's possible, turning science fiction into a rapidly approaching reality. So, where are we with quantum computing today? It's not quite replacing your laptop just yet, but it's already making waves in several key areas. One of the most promising applications is in drug discovery and materials science, simulating molecules, even simple ones, is incredibly complex for classical computers. Quantum computers, however, are much better suited to this, potentially leading to the faster and cheaper development of new drugs, more efficient batteries, and stronger materials. Imagine designing a new solar panel that's twice as efficient, or a life-saving drug discovered in a fraction of the time. That's the potential we're talking about. Another area seeing significant impact is in financial modeling. Quantum computers can analyze vast amounts of market data and potentially identify patterns that classical computers would miss. This could lead to better risk management, more accurate pricing of financial instruments, and even the development of new trading strategies. And then there's cryptography. While quantum computers pose a threat to existing encryption methods, they also offer the potential for even more secure communication. Quantum key distribution, for example, uses the laws of quantum mechanics to create encryption keys that are virtually impossible to eavesdrop on. This is crucial for securing sensitive data in government, finance, and healthcare. The impact on society is potentially huge. Faster drug discovery, optimized materials, more efficient financial systems, and more secure communications are just the beginning. However, it's important to remember that quantum computing is still in its early stages. There are still many technical challenges to overcome before it becomes a mainstream technology. But the progress being made is undeniable, and the future powered by quantum is looking increasingly bright. So, to recap, we've explored the mind-bending world of quantum computing, understanding how it leverages the bizarre principles of quantum mechanics like superposition and entanglement to solve problems that are impossible for classical computers. We saw how qubits, unlike regular bits, can exist in multiple states simultaneously, and how quantum algorithms harness these properties to achieve incredible speedups. While still in its early stages, quantum computing holds immense potential. Experts predict that in the coming years, we'll see it revolutionize fields like medicine, materials science, finance, and artificial intelligence, leading to breakthroughs we can only dream of today. If you found this explanation helpful and want to stay up to date on the latest advancements in quantum computing and other cutting-edge technologies, be sure to subscribe to the channel and hit that like button. It helps us create more videos like this one. Thanks for watching.
I got broads in Atlanta, just took the lean in the family. Credit cards and the scammers, getting no licks in the bank. Legacies.